Hi everyone. We're going to discuss a little bit more about our molecular model of how gas particles behave, and specifically their velocity. So the kinetic molecular theory, remember, gas particles, atoms or molecules are just zipping around constantly, super fast, and the collisions that they have with each other, and then the collisions with the walls of the container are elastic. And so collisions with the walls of the container, that's actually what the physical phenomenon of pressure is. And so we're going to talk about gas velocity, and this is going to be a fairly short uh, content module because I don't think that the calculations that your book does are really, I don't think they really add that much to us. They're just, mathematical manipulations. I'm not sure they will help with the understanding of it, so we're going to skip those. Anyway, so what do we know about gas velocity, ideal gases? Well, gas particles move really fast. And I looked this up recently because I wanted to have an example for it. And of course, different, depends temperature and size of the particle and all that. But a decent number to think about would be 500 meters per second. 500 meters per second. So think about all the gas particles in the room with you right now, oxygen, nitrogen, zipping around at 500 meters per second, colliding, banging into your eyeball face. Oh, I just felt one. Anyway, so that's really, really fast. And then we remember from the kinetic molecular theory that the average kinetic energy is proportional to the Kelvin temperature. And so that's important because kinetic energy, so we'll abbreviate kinetic energy just as KE. Many of you will probably remember from a high school physics class is 1/2 times the mass times the velocity squared. So m is the mass and v is the velocity. And so that's a equation that I'm sure most of you have seen. And it tells us then how much energy there is. But if we know that the kinetic energy, the average kinetic energy for a collection of particles is the Kelvin temperature, directly proportional to Kelvin temperature, then we can relate something to do with the velocity of the particles and the temperature, right? And then the other thing is, look at this equation. Well, if all the particles are at the same temperature, meaning they're all in the same container, there's a distribution of kinetic energies, but the average kinetic energy is that temperature. And so if the kinetic energy is the same, the average kinetic energy is the same, then different sized particles will have a different average velocity. Does that kind of make sense? Because this all has to equal. So that would mean as the mass increased, the velocity is going to decrease. So we could just compare, for instance, let's do helium and oxygen. And helium has an atomic mass of 4 AMU. Oxygen, if you look at oxygen atom 16, there's 2 of them, so that's 32. And so that means oxygen is going to be moving a lot slower than helium when they're in the same container together. Helium's going to be moving a lot faster. So just this is on average, right? Because there's still a distribution that we'll talk about in a second. But we just want to remember, even separate from our understanding of it, that lighter particles move faster on average. Okay, so just again, remember that separate from your understanding of it, and let's take a look at the distribution then of velocities. All right, so this is a figure from the book. It's figure 5.21, and what it's showing is, so this is, you got to look carefully at these when you read them in the book. It's a plot on the y-axis of the number of nitrogen molecules that have that velocity. So it's a distribution, right? It's counting how many nitrogen molecules have that velocity. And on the x-axis, it's increasing velocity. So at any temperature, you know, on the last, so we were talking about, it's the average kinetic energy, right? There's a distribution. So at 273 Kelvin, which is our STP temperature, you can see there's almost a normal distribution of velocities. Some, and remember, they're colliding all the time, so they're transferring kinetic energy back and forth when they collide. But this would be a distribution of it. Some are moving a lot faster than some of the other ones, right? And as the temperature goes up, the average velocity goes up. So look at 1,000 degrees more, 1273. The average velocity is quite a bit higher. And the distribution kind of broadens out. There's still some that are moving pretty slow, right? And then some that are moving a lot faster. And go up another 1,000 degrees, and it broadens out even more. So remembering, of course, kinetic energy is 1/2 mv squared, and looking at this distribution of velocities at any particular temperature. And what we want to take from this is, as you're increasing the temperature, the average velocity increases. Okay, so two things really in this slide to pay attention to. And I know I'm repeating it, but I want to make sure we understand it. The distribution of velocities. So you've got distribution of velocities with the different molecules at any particular temperature. But then as you go up in temperature, they're on average moving faster because the kinetic energy is higher. All right. This is actually an example that they had that I had to find in the book. And what I wanted to do, because on the first slide we talked about the velocity of particles and the relative velocity based on the size of them. And so this is the only figure of that your book had. And so it's the same data as the previous slide. We've got velocity on the x-axis, so we're just increasing this way. And again, you know, a count of the distribution of molecules that have that velocity. Now, the difference here is that it's the same temperature, but we've got two different molecules. UF6, which is a humongous and very, very heavy, right? Look up the mass of uranium, fluorine times 6 and add it together, compared to hydrogen being a mass of 2 AMU. So they've really drawn the contrast here. These are at the same temperature, and you see how much slower the heavier molecule is moving on average than hydrogen. Hydrogen, you've got this, I mean, some hydrogen molecules are moving the same speed, the same slow speed, but it's a distribution all the way out to here. And so when you do this at the same temperature, that means the average kinetic energy is equal, right? So if these are in the same container or held at the same temperature, their average kinetic energy have to be equal because that's what temperature is. And because of the kinetic energy equation, and you can hopefully just remember this, but you can also figure it out. So if this average kinetic energy is equal, as the mass goes up, the velocity has to go down, right? And so this heavy molecule UF6 is on average moving much, much, much slower than the hydrogen molecule. It's zipping around because it's so light. So light things move a lot faster. Okay. Next, definitions. Your book has calculations on this, and we're not going to do any of the calculations. I just don't think, I mentioned that at the start. I don't think they're that worthwhile. But I will do the definitions because they're relatively easy then to know the definitions. And you know, diffusion is a word that you've heard before, I'm sure. In the context of gases, and both of these words are talking about the movement of gases, the movement of gas particles. Diffusion just means mixing of gases. So if you open a container of pure perfume at the front of the room, the gas will evaporate and spread throughout the room, and you'll smell it in the back of the room. And that's just diffusion of gases. And they tend to move from high pressure to low pressure. Things don't move from low pressure to high pressure unless we have a pump. And then effusion is a more specific form of this. And there's a figure in your book, figure 5.22. It's not showing up great here, but you have the handout and you also have the book. And all effusion is we're going to have a little pinhole, and we're going to let the gas diffuse through the pinhole. So that's diffusion through a pinhole, or a very small opening. And I think I'll write it on here just to so that nobody misses it, even though I said it. We're going to skip the calculations. And I think that's on the study guide for the chapter, but I'll try and make sure. And again, we're not really doing anything different here, just the definitions: diffusion, effusion, and the same principle as those velocity distribution plots that we were just looking at. The same principle applies. The larger or heavier particles move slower. And hopefully that makes sense. All right, that's it. Fairly short content module. Let me know if you have any questions. Thanks.